first. Hello, everyone, and welcome to the fifth session of the EMEA Academy. For those who are new here, we would like to introduce you to the EMEA Academy and what is it about. So it was an initiative from the Young Water Professionals of the Modeling and Integrated Assessment Specialist Group of Iowa, and it's meant to be a guide for those who are interested in modeling and do not really know where to start. So it's going to be it's a series that started in November last year, and it's still continuing till today. We've went through the activated sludge models and what are models and clarification models, physical chemical models, and right now we have Janelsi, who's going to walk us through a very important step in modeling, which is data handling. Janelsi, the floor is yours. But you have it in presentation mode, I think. So maybe you can just switch display settings, I think. If you have a second screen, I think, or something like that.
Can you see correctly the presentation mode?
We can see the next slides and the notes also.
Okay. Let me change that. Let's start again.
I think it was in display settings if you swap presenter and slide, yeah.
It's okay now? Yeah, okay, great. Thank you for the introduction and hello everyone. I am Janelsi Alferez and I will be talking about data handling, transforming data into a strategic asset. So a little bit about myself. I am currently a R&D researcher at Vito. Vito is a research institution in Belgium, and I have been working in the last more than 15 years on topics always related with the digital water technologies, covering the whole data pipeline from sensoring, instrumentation to automation control and decision making. And I am part of different associations like the ICA Specialist Group and also the Water Europe Expert Group, also on digital water technology. So it has been always around the similar topics. And my big interest is on how to bring actually research into practice and how to implement data-driven solutions in practice. So I wanted to start this presentation thinking about what is data handling and why this is relevant in the water sector. And for that, we can start from the beginning, thinking about what are actually the current challenges that we are facing in the water sector. We have many, and we know that from an increase in energy consumption, we know that we have actually a big challenge related to climate change and the water stress, and more aging infrastructures on the drinking water side, but also on the wastewater sides, and an increase, of course, on water demand in the years to come. So it's a reality, and I think by now we are mostly all aware that we cannot manage or we cannot face the current challenges with our current infrastructure, but also with the current way on how we operate our water systems. But that can sound negative, but at the same time, that give us quite some potential for savings and also to improve the way how we operate our water systems. It's also a reality that we are collecting more and more data every day at different levels of the water cycle. So at the water treatment, utilities, drinking water, also in industries, information from irrigation, groundwater. More and more we see the deployment and the installation of sensors that are collecting high frequency data And that data, of course, is needed to describe, for example, and detect pollutant dynamics. This is more and more relevant to ensure water quality directives that are also becoming more restrictive every time. But also the information that is collected can show or highlight opportunities to improve the management of the different water systems, and also highlights probably certain mitigation actions that we can perform. And of course, data is there to increase public awareness and to also put forward cooperation between stakeholders. This is actually a big issue at the moment. We see that water cannot be seen as a siloed system like it was in the past, and is part of a bigger ecosystem where we make the link with energy, with food industry, etc. So we are collecting more and more data every day. And that's clear, of course, that we are going through a transformation at different levels of the water management. We really are needing and looking for more efficient and robust and sustainable systems. And in parallel, we have actually a huge development of technologies, or more on the digital side. So we have a lot of monitoring and sensory technologies, ICT, modeling. More and more we hear about AI, data-driven, machine learning. So it has been a huge increase in the last years. And we see this transition from data towards more intelligent actions. So we are really talking about going or transforming raw data into actionable insights. And in this history, data is really a core element. Data is really the foundation to go from data to more wisdom or more advanced knowledge. So maybe let's dive a little bit on this framework. This is a known hierarchy that is utilized in different domains. So where we see that it's a bottom-up approach, and the value that we can get from the data can increase on this pyramid, going from data, so that we are collecting from our processes, towards having some sort of information that is coming from the measurements, and also how we can create some knowledge or some further insights based on that information, and at the end create some wisdom or some more smart decision making. And of course, the value of the data increase the more we go to the vertical side of the pyramid. We also see on the figure on the right that the added value in the data will depend as well on the level of processing that we apply to the data. So whether we go from raw data towards more refined insight or more highly processed data, we increase, of course, the value that is on the data. So if we apply this to the water domain, we can see that in our bottom layer we have whatever water system or water treatment technology that is generating data from sensors, for example, but it could also be from measurement campaigns, laboratory measurement, etc. But here, what counts a lot is really information collected from sensors in those systems. Then those systems are generated information. We have data that is being collected by the sensor, but also all the ICT or IT infrastructure that go with it. And that information can be fed, for example, to develop process models and create digital twins. And after that, we go a step further to have a smarter decision making, and have, for example, more automatic control or optimization strategies. And as mentioned before, the more we go to the top, higher value that we will have on the data. So if we think about this framework, as I mentioned before, it's a bottom-up approach, and also the availability of good data is an enabler for the framework to work. Otherwise, we will never go from data to really insights and smart decision making if the data is not representative of the system that we are monitoring. So data plays a core element for the application of whatever data-driven solution we want to implement. And also it will, in that way, if we apply it correctly, it will accelerate really the transition towards a more efficient and sustainable systems. So if we think about any physical water infrastructure, for example, a drinking water treatment plant or a water resource recovery facility, data is actually present everywhere and can give us some added value along the whole data pipeline. So we have the sensors that are generated information. That information can be utilized, as I mentioned before, to create or develop some digital twins. We can also think about creating virtual or soft sensors, also using that information within controllers strategy from the traditional to the more advanced ones. Also on how we display that information, generating like better insights for the users, and how we support the user in whatever decision making. So data can have really an added value along the whole data pipeline in any treatment process or physical infrastructure. So when we talk about data handling, we are actually talking about going from data that is being collected in different sources, in different means, towards a process where that data gets organized somehow. And that data should be also validated to be sure that it's correct and it's representative of the system that we are monitoring. And after all the processes are carried out, we can talk about using the data for example, further machine learning approaches to create digital twins or models and for further automation or optimization strategies. So, but we really need to go from top or to bottom to top in order to be able to use the data in a proper way. So it's really a process of several phases of collecting, organizing, cleaning, and of course, analyzing the data and going from raw information to really produce actionable insights and of course, structured data. I think only in that way we can really turn this raw data in data that is representative, that is reliable, that we can interpret, and that we can really use. And this will help us in the whole data management strategy that will help us to make data more interoperable, to automate decision making, and at the end, to save cost and time on how we handle the data. So all this sounds really interesting. However, there are quite some challenges to make data handling really applicable and efficient in practice. So in one side, we have technical challenges. I have put here a few, but there are many others. But I wanted to highlight this one because they are really visible and present in many water utilities at the moment. So we are collecting data by several sensors. There are water utilities that have really a broad, high number of sensors installed, but there is not a lot happening with the data, and we have actually data graveyards and silo systems. There is also not information or data about that data that is collected or being produced, and there is, of course, the presence of poor quality data. That's more on the technical side, but we have also some other challenges that are more, I call it not technical. That is, for example, the lack of governance that explain how we work with the data, who is the owner of the data, where are maybe there is lack of resources or lack of skills. That's an important point. We see more and more that the skills, even on the operator side, need to evolve toward more data-oriented work. And the last one, I think, is a really key one, that is the fact that putting figures or numbers and what is the added value of having a data handling strategy is quite difficult. So yeah, convincing, for example, management that this will have some high ROI in certain years, that's a quite difficult matter. So there are quite some complex challenges in practice, and the truth is, what is currently happening is that there are not really best practices that guide us on how to go from the data collection to how we organize the data, how we validate the data, and how we can further use it for different applications. So going from data collection to really being able to use that information, we need to get value from the data in order to apply that framework. But in order to get value from the data, we need data quality. But also to assure data quality, we need to have information about the data. And that's allowed me to introduce two main concepts. So one concept is about this information about the data, and the other concept is about data quality verification. So maybe let's start with the first one. What is this data about the data? So that's what we call in the data world metadata, and this is actually pieces of information that describe several aspects of the data itself. First, how, where, when, and why certain data was generated or maybe modified, how this data could or should be interpreted, what is the quality of the data, what is the level of confidence that we have in that data that is collected, and also some maybe contextual information regarding how that data was produced, what is the purpose, or for what we want to use the data. So metadata is really seen as the key to unblock the value on the data, and it's quite dependent on the collection system, on the data collection system, and how this is implemented. So that's why it's also difficult to put some best practices on how to generate this metadata and how to deal with it. I wanted to give some examples on what is this metadata. So imagine we have the figure in the left. This is a time series of dissolved oxygens that is generated quite some high frequency measurements. And we have assumed we take one single value from that time series and we get the value of 2. But what's this value tell us? Not a lot. How can we interpret this value? So we need to add some further information. We can add some units, so in this case, milligram per liter. We can also add a timestamp when the measurement was taken. We can also actually include what was the principal measurement, the measurement principle, sorry, of the sensor that was used to collect this information, where the sensor was located, in this case, an aeration tank, what is the model of the sensor, and maybe we have some accuracy information on how the sensor is performing. And in this case, we know that this time serial sensor was used within a control loop. So we really need to know a lot more to be able to evaluate the information contained in the sensor signal. And that's what we call metadata. So we have seen the example before that is related on giving us information on how is the signal that is generated and also related to the device that is generating that signal. But there are other type of metadata that account, for example, for more dynamics and sensor behavior. An example, this is the response of a pH sensor when it's put in a buffer solution. We are able to measure the response time. This is actually an important information because it can give us it can give us information on some aging of the electrodes on the sensor, or maybe the need to perform a calibration, etc. So this is also part of what we call metadata. And there is other metadata that is related more to how we give context to certain events or causes. It's not numerical data, but it could be a note, it could be some text that is added in the example in the right. So one have written down that the OUR have dropped significantly, and also there is a reasoning behind. So all this, what you see in the three examples, is actually part of what we call data about the data. Of course, there are so many sensors out there, each of them collecting data in a different way. So data is quite heterogeneous, and this could be quite overwhelming to know how we start and how we collect this metadata, what is relevant or not. So we really need a comprehensive overview. And at the end, what we need to represent somehow, to illustrate somehow, is for every single data point that we are collecting from a sensor or that we are analyzing from the sensor, we need to know what it is, when this measurement was taken, where, how the measurement was acquired, what is the quality on that value, what was the purpose, and maybe some context. For example, was this taken during a training event, or maybe there was a calibration, all that give context to that value. So to help a bit on this starting point, this was actually the goal of the MetaCo task group that is part of the RCA specialist group. So there was a big effort to try to put together different pieces. This was a collaborative effort with more than 100 members, from researchers to practitioners. 1/3 of the people involved was really from water utilities. And the goal of that was really to clarify metadata concepts, really describing sensor signals, in this case for wastewater treatment plants, and how to obtain that metadata. And at the end, there was also some guidelines on how to implement such metadata collection to facilitate, improve decision making. So I think this is a great starting point to start diving on metadata and understanding how can we produce, what are the different type of metadata that we can have, and how we can actually take that information into account. So you can have a look in the link that is there, and there are several chapters. One chapter is really dedicated on describing metadata itself, but there are other chapters that are really with the focus on how we implement methods to evaluate the quality on the data and the metadata associated to that. So that report that is out, it was out at the end of last year, give us a really comprehensive overview on how this metadata can be organized. And it was decided to classify metadata in 3 main categories. So one of them is all metadata that is there to describe signal generation, for example, how the signal was produced, information about the device that is producing the signal, and maybe if we have some modification of that signal, for example, if we apply some filtering or whatever other maybe modification we did to the sensor signal. There is another big group of data that is there to describe sensor data quality. For example, how we can describe measurement errors through symptoms that we see in the data, but also how we can describe measurement errors through causes that we also see on the data. And of course, different methods to diagnosis and to identify the different causes of the errors. And there is another big group that is related to what I explained before on metadata that provide contextual information, and that is would really be helpful if we want to make use of the data for different applications. To go a little bit further on that and give you a few examples, when we talk about signal generation, we already few some examples. We are talking about, for example, information about the sensor location unit, but also on how the data was transmitted. If we have a log about maintenance, if there is some signal processing involved, so it's really on how the signal was generated. And then we have other set of metadata that describe more symptoms on the data, either more static characteristics, and more dynamics. For example, we talk about accuracy, precision, sensitivity, and on the dynamic side, more on response time. That example we saw before, if there is the presence of drift, or maybe some outliers. And also if we manage to see or classify data coming or with the presence of some systematic error, gross error, random errors, and some help on how to detect and link the causes to the symptoms. So there is an extended definition and explanation of all this in the STR. So for the ones that are interested on the metadata topic, I invite you to have a look at the STR. So now that we have learned a bit on what is data, this data about the data, then the next question is why and how we account for data quality. We have mentioned data quality a few times, but let's dive a little bit more on what we mean with that. So we talk about data quality, especially in the water sector, because this is about how reliable is the data that we are collected. And the truth is that in the water sector or in the water environments, these are known to be hard measurement environments. We have really hard measurement conditions. And that makes that the sensor or the measurement from the sensor get degraded in time, sometimes sooner than others. And that's due, for example, to agents or drifting of the sensor electronics. This could be some falling and clogging of the sensor, as you see in the picture on the right. These are a reality. These are coming from real implementation of sensors in treatment plants, for example, and wastewater treatment plants. It could be as well that there is not maintenance applied to the sensor, and at the end, the measurements are getting degraded. So we can have, for example, the presence of drift or really some big failures like frozen values, the presence of bias, or really degradation of the measurements. And this is a reality. In fact, we know that more than 50% of the data that is collected at the treatment and the wastewater treatment plants, for example, are of bad quality. So from all what is collected, half of it cannot be really used. So the fact is that data should be accurate. We should be able to verify that the data is correct. So that data should be properly validated. However, the common situation is that data quality or even the concept of data quality is often overlooked and not even the more basic questions are answered. For example, do we know if the correct data is being retrieved? Do we know if the signal quality is checked somehow? Is data quality a non-issue? Are data quality procedures applicable or even being used? Sometimes this is not even known between the same people at any water utility. And maybe also the last point is important, is this data quality made available for the users of the data. So the truth is that still the common practice to check data quality, if it's being checked, is still visual inspections through different, for example, Excel files, or through different dashboards or manual procedures. And the fact is that faulty data, if we work with faulty data, this can be quite critical when we use the data, for example, to take decisions, when we use the data for modeling approaches, or even in automatic control strategies. So that could be quite risky if we don't deal properly with this faulty data. So when we talk about how to really handle the processing of data coming from raw data to more validated data, there is several steps of different phases that need to be taken into account. So in the first phase, we talk about preliminary analysis. So as soon as we receive some data and we are collecting some data, we can have already some preliminary analysis with some simple visualizations like time series, histograms. We can maybe group that data depending on operational conditions, whether it was a dry or wet seasons. And we can also have some quite simple descriptive statistics being calculated to have acknowledgement on how the time series look like. We can go to a second step where we apply already some data preprocessing. Here we talk about removing outliers, also dealing with missing data, filtering to remove noise, some transformation or scaling, and adding some structure to the data. And finally, we go to the last step or the last phase, where we apply some data quality analysis. And there are different methodologies and approaches that can be utilized for this. We will dive a little bit more on that later. But there is a quite broad possibilities on what we can apply to evaluate data quality. So then we managed to go from what we call primary or raw data to more advanced or secondary data, where data had been actually validated. However, there is not really a single valid pipeline for all cases, and the truth is that this pilot pipeline for data processing is case specific, and only few facilities have really implemented real-time automated raw data processing. As I mentioned before, most of it, when it's done manually. And all the data, good or bad, is being recorded in a data management of some kinds. And most of the time, this data processing step is not included in the time at the time of the collection of the data. So now that we know a little bit more on what are all the steps needed to go from raw data to validated data, we can also dive a little bit on what are the typical issues that we encounter on the data that affect its quality. So we talk a lot about outliers, and you see in the two figures in the top and in the bottom, outliers are really anomalous observations that when you compare with the rest of observation, it's clear that these are not part of the same, or that they behave different than the rest. So in the figure on the top, we see this is the case for univariates, or we look at one variable at the same time. So any X concentration, and we really see a value that is really out of the normal situations. The figure below is more multivariate approach, where we look at two variables at the same time, for example, and we have the cloud of points that describe a normal correlation between the two variables, and clearly a point that is out of this normal situation. So that's clearly an outlier point. But we also have the presence of noise data. This happens quite often when we talk about sensors. So these noisy data are really inaccuracies or fluctuations that can be due, for example, to environmental factors, maybe some hardware limitations, or even electrical interference that make add some abnormal fluctuations on the data. So this is an example for DO. This is a really noisy data, noisy time series. If we apply some noise removal, in this case, a moving average, we see that now the dynamic of the DO becomes evident. So that also shows the importance of removing noise on the data. And there is also another quite typical issue, that is the fact of having missing data, so data that is absent. This can be due because of the sensor was outside detection range, or maybe there was a communication hardware issue. So we encounter this issue like quite really often. But there are ways to mitigate that, so we can actually estimate the pieces of missing data through different methods that is part of the what we call data imputation. So wherever the fault or anomaly data that we might find at when dealing with sensor data, or in general with time series, there is a framework on how we can assess the quality of the data being collected, and the path to implement different steps that I will describe now. So the first step is really to identify what are the needs. So for what are we going to use the data, and what type of anomalies are important to detect. Second step is how we identify the data characteristics. So what are the dynamics? Do we have historical data that we use to understand how this data behave? And what are really the intrinsic dynamics? Then how we can link the anomalies to the symptoms. What would be, or how can we prioritize the anomalies? If we have a list of anomalies and we have to tune our method or our solution to detect few of them, what will be really the consequence of not being able to detect certain anomalies? How we can evaluate if our methods or our models that are used to validate the data are performing correctly. So we need to define some performance metrics. And an important step, we need to select the best methodology possible or the best method available to really assess the quality of the data. And this is not a simple task. Here, we need to take into account the characteristic of the data, for what the data is going to be used, and maybe this is about choosing between one or two methods, but actually implementing a combination of them. We have to describe some pre-processing requirements, of course, that will depend on how the data look like and how to evaluate the method performance. And for that, we might need to calibrate, validate, and test the method before it is applied. And in all this process, the domain experts and the knowledge from domain expert is really crucial, and also to involve the users to be able to actually tackle what are the needs for what the data is going to be used and understand the dynamics of the process. So if we see this framework, this is mostly related or oriented to have an automatic data validation. As mentioned before, what we encounter most of the time are really manual procedures, and due to the amount of data that is more and more being collected, we really need to move towards automatic data validation. And this framework is there to actually guide in that regard. So I wanted to introduce a bit on what models, what techniques can we apply to assess actually the quality of the data being collected. This is maybe a busy figure. We are not going to dive in the different blocks, but I think it gives an interesting overview on the available techniques that we can use to actually assess the quality of the data that we are collecting. So there are, I would say, three main categories of techniques. So in one side, we have the techniques that are more called or based on mechanistic understanding. So the one in the right. These are methods that are used when we have fundamental or we know fundamental relationships of our data. If this is not the case, we have another big category that are methods that are more based on the data itself. So they are called statistic and they are based on statistic and data analysis. So they are really data driven. We don't need to know fundamental relationships in order to apply those techniques. And we have, many of them available, and they will actually depend on how we use it, will depend on the data that is available. Those methods, either they use, for example, what we call a learning process that is unsupervised or a learning process that is supervised. And this has to do with the presence of nodes of real labeled data where the real anomalies are known. And this is quite a difficult task. And then we have another group of classification, let's say, that is related to whether we have, for example, known correlation between different variables, whether we are looking at one particular variable at one time, or whether we are looking at a set of variables. So we are talking about having spatial correlation. So these are the three main categories, I will say, that we will find out there concerning techniques for assessment of the data quality, and three main decision points that will guide us on what to utilize. So either we have knowledge of fundamental relationships, whether we have level data available, and whether we have the presence of strong spatial correlations. And of course, you see that there is at the bottom of the figure really specific methods to deal with each of the type of classifications. So it's quite broad, but I think this gives a nice overview on how to start and where to go depending on the information that is available. So maybe let's just to dive a bit on some of them. We talk about the first group. There are the mechanistic ones that deal with mechanistic understanding. And here we have two possibilities. We have the method that only look at one variable at a time, so the univariate ones. And for that, we can just apply really simple tests on the data to already identify some anomalies. For example, we can check whether the values are beyond certain threshold, whether they are out of the range of mix and max allowed values. We can verify if the data is changing too fast or too slowly. That is about rate of change. Maybe there are some frozen or constant values, and that's something that we can check quite easily. And this will already allow us to identify the first type of anomalies that actually are quite, visible in practice. We have many of those in practice. And at the end, those simple tests can also be implemented in control charts when we monitor each of the tests and we define certain boundaries, and where any time that we have a value out of the boundaries, we already know there is a certain anomaly going on. So these are the more, I will say, straightforward methods to implement and to check. We have an important one that are what we call sanity or plausibility checks. This is also that we can apply all the time, and that should be actually the first implementation. These are actually checking I would call impossible data. So we know, for example, that concentration cannot be negative. We know that total COD cannot be lower than soluble COD, that total nitrogen cannot be lower than soluble nitrogen, and this type of relationships that are quite like physically impossible. So this already can give us some information on anomalies that are really quite easy to detect. Then we have, based on this mechanistic understanding, if we have several time series available, we could apply a more multivariate analysis and talk about mass balance. This is quite used when we work with models. And for that, it's based, of course, you need to know the fundamental relationships and the equations behind in order to apply those mass balance. As soon as the mass balance is not close for certain variable, we know that there is already an issue with the data. So, depending on the method we apply, this output of the method can be seen in different ways. It could be that we give a quality stamp to each data point, or we could talk about confident values. So we give a number that indicates how confident we are on the quality of the data. Then we pass to the more statistics or data analytics base. And in here, as I mentioned before, The difference is related to the type of learning and the fact that whether we have or not what we call labeled data where the anomalies are known. So we have in the first place supervised methods. So in these ones, we make use of labeled data, and this is used as an input to train the models. So those methods are, I would say, quite easy to implement, but the difficulty is to have the label data available. Normally, building label data take quite a lot of effort, quite a lot of time, and it's not that straightforward to obtain. But if we have it, some of the examples of the methods that are used are, for example, all what is about regression approaches and also classification approaches. Then we have the other family on those methods that are called unsupervised. In these ones, we don't need any any label data set, so we just use the time series that we have from the sensors. And the two main groups of solutions are, for example, the one that deal with clustering of the data and also dimensionality reduction, for example, the well-known PCA. So these are, you will hear a lot on supervised and unsupervised methods. And I think the important is to have clear that their use really depends on whether this label data is available or if it can be available. And then we go to the third classification on whether we are dealing with univariate versus multivariate methods. I'm giving here some examples that we are working on them. So the first one is related to univariate methods. So in here, the goal is really to flag anomalies in single time series. So we look at one time series at a time or one sensor at a time. In these implementations, we apply different single tests and also not only physical ones, but also statistical. So we were checking different characteristics on the data on the statistical side, also on variability, on rate of change and range. And the idea was to detect, for example, anomalies related with a normal variance or no variability on the data or sudden change that are out of normal. And in this approach, we combined the different tests in one single output that we call the overall validations. So for each single point, we have a stamp whether that data has been considered valid or not. You see some examples in the figures, how we can indicate, for example, data that is the okay values that are in green, and also maybe some warning values where maybe the confidence is not that high, and some critical values more in red that are really real outliers. We can also see that information more on confidence value. So the higher the confidence, the higher the trust that we have on the data, and the lower the less. And we can also see, for example, some details on what tests have failed each time that an outlier was highlighted. So this is really, with the focus on identifying anomalies of abnormal data in single time series. But then we have other type of approaches that are the more multivariate ones, where here we look at several variables at the same time. In this case, the goal is to identify, for example, anomalies that might be affecting several sensors or that are somehow breaking the correlation that we have between a group of sensors. One well-known, and I will say one of the most used one is the PCA, and there the monitoring of the anomaly is a little bit different. We use some what we call multivariate statistics to detect anomalies, and those multivariate, two of the most known one are the SPE and the T-square statistic. They give information on how our data is is behaving according to the PCA model that was created. They can also give information on how the variance of this group of variables have changed. And so these two statistics are used to highlight situation in whether this correlation is broken. So these are an example from for a specific period, we have the two statistics already showing some situations where there were some anomalies detected, and if we see in the figure in the bottom at the different single time series, we clearly see that in those specific moments there were something happening at the treatment plant, in this case affecting actually several sensors at the same time. So this is just to illustrate how those methods can be used and what sort of information can be generated. So we have covered a bit of some of the main techniques that are out there. And maybe the question now is, what can we consider when we talk about data quality, on how we implement this approach? The truth is that this is more a ad hoc trial and error approach. So there is not a single solution. Sanity check and not balance should always be applied if possible. This will allow us to detect some gross errors. Historical data should be, can be exploited if we implement methods that are really based on data. Everything will depend on what type of data is available and also how we want the outputs of the validation method to look like. Independently of the type of method we use, we always need to apply a process where we validate the methods. So we start selecting some data set for training, and also based on that, we need to tune the method. So we need to calibrate it and then validate that method and see if it's behaving as we want. For that, we have to define some performance metrics, check if it's behaving as we want, and this is not the case. We need to retrain until we have an acceptable behavior. Two important points I wanted to highlight: the proper setting of any algorithms we want to use. It will really have an effect on the output of the methods. And another important point is that we need to have proper data sets for this calibration and validation. We need to cover operational and dynamic changes in order to make our model valid. So this is also another process that needs to be taken into account before we really implement any method in practice. So maybe what other practical aspect we should consider? I show you a figure with many methods, but the truth is that all of them, they have their own strengths and limitations. They are not exclusive. The output of the methods can be represented indeed as a label, as a quality score. And the truth is that in practice, in many water utilities, what is used at the moment are the univariate control charts. That is the easiest to implement and is what most of them use today. If we go to data-driven methods, we will require larger data sets with large variability in order to use them properly. The use supervised method, as I mentioned before, have been more extended because we don't need really these level data sets. So you will find more of them in practice, and process knowledge will always be required for any implementations, and also to properly setting up the validation approach. Just shortly, I wanted to make the link again with metadata, because if you remember, we have a big category on how there is certain metadata that describes sensor data quality. So all the methods that we saw before can help us to identify, for example, some symptoms in the data. Either we have some presence of outlier, do we have some bias, some inadequate response time, some drift. But the difficulty is to actually match the symptoms with the root causes. I give an example with the outliers. Imagine we have identified an outlier with one of the methods, but do we really know the cause of that outlier? It could be an instrument error, but it could be because there is a wrong recording or a wrong reading. It could be even because there is some electrical noise or magnetic noise. So this link between the symptoms and the root causes is not simple. And there is still quite some work to be done. And I wanted to highlight that that makes actually more relevant and more relevant the fact that we really need to have in place operational methods to implement and operate the sensors in a proper way, combine it with tools to validate the data that is being collected. Almost closing, we have seen the importance of the data, the importance on the data validations. That all sounds good, but in practice, when we discuss with the water utilities, these are some of the messages we get from them. For example, I still cannot get someone to clean a sensor once per week. So that's a big issue related to maintenance, how we can have proper data if maintenance cannot be made. They are still using spreadsheets to collect verification readers. If we talk about metadata, this is always part of the umbrella of data management. That is still a big challenge for many utilities. So when we ask the utilities what will be for them the next steps or what they would like to see is things that are easy to implement and as automatic as possible. I think that's a good remark. Assign ownership for every single task, data related, connect people with data, and make sure that the value actually lies on making the data useful for a particular purpose. So to summarize, as a take-home message, you remember the figure I showed at the beginning. So data handling can really support the proper use of data along the whole data pipeline in any water system. When we talk about this physical sensor collecting data, we can talk about monitoring network, but even further toward remote sensing. We can be using the data within digital twins for forecasting or for estimate certain parameters. We can use the data to elaborate advanced dashboards with advanced data analysis. Use the validated data within really advanced controllers like model-based controllers or reinforcement learning controllers. And finally, to support really decision making. I think that's quite clear how validated data can be useful at the different stage of the data pipeline. So as a take-home message, data is really a powerful resource. If it's correctly handled, is as the case, we can really use it towards growing on smarter water systems. Good practice should include the collection of metadata to know different information about the sensor signals, what is the data quality of the sensor, and to give some context of the data collected. The method for validating or assessing the data quality is they are quite broad and they can be quite case and purpose specific. And most of the time, not one single approach is the best one. And it's mostly about a combination. We can think about combining simple methods with more advanced. And of course, this has to be properly set up to have better results. Still, there are quite some gaps to be overcome. Some of them are quite technical. This include, for example, lack of standardizations and lack of automated procedures, but I think we are on the good track and in the good direction on that. And as a final remark, metadata and data quality verification, I think they are really a must with any or within any data-based applications. And this includes every time that we want to work with models or digital twins, control strategies, or decision support. So I think with this, I finalize. And thank you very much. And if there are some questions, I will be happy to answer.
If you have some questions, you can put them either in the chat or you can just speak up.
Hi, this is a really good, very systematic presentation. Thanks for this. I have two questions related to two different topics. The first one is the metadata. So for the metadata, I have, again, two questions. First of all, is there any standard minimum requirements of metadata to collect? And the second question is metadata collection could be expensive. For instance, like in the storage, for each of the data, we need to store like their units, like their timing of collections, etc. Is there any suggestions on the metadata storage or the data schema kind of like optimization so that we can save the money? And I also have a question over the multivariate data cleaning over here. So for some of the time series, the sensors locates at different locations. Some sensors in the influence, some sensors in the aeration tanks. There are hydraulic delays within those like sensor readings. How do we handle those in the multivariate part? And also for the multivariate methodologies, it is not easy to, it is give like PCA, it just give you an overall, like tell you at this point, all the data got some issue. How to contribute which actual signal has issue using during those multivariate methods.
Let's see if I remember the first one.
Oh, okay.
Yeah, so about metadata, indeed, I think I will recommend to have a look in the STR, because in there was a big effort made to list what exactly your question, to list what is really the minimum data that we should take into account when we talk about metadata, and also on the different types of metadata that could be considered. And I think that will be the first step. This will be also related to your application. What really makes sense for your application? Because there are, I can tell you, like hundreds of different types of metadata that we could apply. And this is a lot indeed, but maybe we don't need all that. So it's really have to do with your own applications. And I would recommend to have a look at that, because it's really a long listing that was done. And there is also some information on let's say more, I call this more infrastructure wise, on how this metadata can be collected. It's not simple because there is not a standard way to do it, and this is one of the main bottlenecks. This is a question that we didn't manage actually to answer totally, and at the moment there is a working group to have a continuation on that, and be able to help to create some guidelines on how this could be implemented in practice. So we have the starting point. This is the metadata that is relevant, how we can link this with the applications, what methods can be used, for example, to generate metadata related to data quality. So that's the first thing to be done. But it's true that there are other, some questions coming, some other aspect to be considered. So for that part, I will recommend to have a look in the STR. There is a big chapter on implementation, but not all the questions are answered. We gave some guidelines, but the difficulty is that it's really heterogeneous what you can find out there, and this is one of the main issues on the water utilities. The same question that you have now. Okay, this metadata is relevant. How and where we collect it? And this is growing toward more IT and data structure wise. So there is some information there, but not all the answers are there, I have to say. And the other one was about the
delay in
yes. Yes, about the multivariate, that's true. So I don't have a complete answer for that. Some methods will deal better with that than others. Concerning the PCAs, there are at the moment, you have in the other question related to what variables contribute to the faults. There are some sharp analysis that can be performed, and also some fault isolations steps that will help you to identify, okay, from the output of the PCA, what is the sensor that is causing the fault. But even there, it's not that simple. It doesn't perform well all the time. So that's also another challenge when we apply this in practice. Identifying the root cause and the signal that is causing the fault is not that simple, but at least we know that for example, if a multivariate a statistic is flagged, we know, okay, there is a problem, we need to look at the sensor. At the water utilities, that's how it's being used. Whenever there is any multivariate approach being implemented, that is really few of them. So the multivariate statistics are there to show you, okay, there is an issue here, and then the operators go to have a look on the sensors in that period of time. That is the easiest way to do it at the moment, because there is not a 100% approach where the outputs are 100% reliable on what was the causing issue. There are some methodologies, as I say, the char values is one that is getting more and more in place. And I will say that could be a way to go in that one.
Oh, thanks.
There is a question in the chat from Sophie. She asked, or she says that she needs some data validation, but for a large data set with steady state data from multiple treatment plants. Do you have any specific recommendation for that validation procedure?
Data from different treatment plants?
Yeah, steady state data from different treatment plants.
Oh, and when you mean a steady state, you mean are there not important dynamics? Or can you elaborate a little bit further on that?
Sophie, do you have any further explanation?
24-hour reports. That's okay. So the amount of data is not that high, if I understand correctly. Well, it depends. It depends on the amount of data. I think any method will perform as soon as there is enough information. If we want to apply data-driven models, we need to have some consistent amount of data in order to be able to have some representative results. So to give you an example on that, we have used, so it's not impossible because we have used data-driven models not to detect anomalies, but to, for example, fill the gaps of lab values. So it's really also really not with high frequency information really to fill gaps on lab values. It's the same type of method that is only used with a different purpose. So I would say it depends on the amount of data that is available in that regard. But in the same way, you can apply for, it could be, I don't know whether the treatment plans are related. I don't know if they belong to the same physical area, is the idea to find correlation between them. So it is more, I guess it's more on that regard on the multivariate side. So I think, I think many of the methods will be applicable, but it will depend really on the amount of data that is available. Maybe also to comment on that, in the STR that I mentioned, there is a big chapter that is part of what I show also today, a big chapter on these methods for data validation or assessment of data quality. And there we put forward actually, several aspects to consider to guide you a little bit on what is the method that will fit maybe the most specific application. So in that regard, maybe it would be good to have a look on that. Mhm.
Any other questions? I maybe have a question that's not maybe very related to data handling, but you mentioned that you saw that you heard that there's a lot of issues with, for example, sensor cleaning, that people are
Mhm.
not motivated to do that on a regular basis.
Mhm.
Do you have any solution for that? How to get that done?
That's also an interesting one, because I think there are different angles of that problems. It has to do a lot, I think, with the culture of the culture of the treatment plants, for example. That is where you see most of these problems, where data quality have never been an issue, or have never been something on the table to really look at. So there is not maybe needs to take care of the data of the sensor. So sometimes that it only happens when really a sensor is broken, and you don't realize that the data from the last 3 months is not useful anymore. So they have to be with the one of the aspects is really the culture of the organization of the treatment plant or the water utility, to place really value on the quality of the data. Another important point is to have really a standard protocols or standard procedures on how to do the checking on the sensor and the maintenance. Maybe certain sensors only need to be checked in a certain moment, in a certain period. So we can optimize that maintenance routines and that maintenance activities, but not even those standard protocols are there. We in this work related with the STR, we discussed it with many water utilities, and there were only really few applying standard protocols. Some information was quite basic, while others are more advanced on that. But we are still at the level of not really, as you say, cleaning properly the sensor. And then we are talking about implementing AI, having models, etc., where not even the basic aspects are being done. So I will say these two things: the lack of standard procedures, and actually the lack of more culture or database culture within the water utilities.
Okay, thank you. Is there any other questions? Okay. If there's not, I think we can end the session here. I would like to end by thanking Janelsi for the very interesting presentation. And there is a question.
Can read it partially.
It still comments on the question of Sophie. Okay. Yeah, I think we can end this session here. So thank you very much for the presentation and the answer to the questions. And
Thank
hope to
you.
see you in the next MIA Academy. Bye, everyone.
Thank you. Thank you. Bye bye.